Hello and welcome to our discussion on dual in linear problems. Now in last lecture we saw what is the relationship between primal and dual. The relationship is that if we change the perspective, if the objective function somehow becomes constraints and constraints become somehow objective function, then what is the relationship between primal and dual? Today we will be seeing how to convert a primal into its dual. So for the purpose we will be taking an example, and let us say that example says Zmax is equal to 4x1 plus 3x2 subject to certain constraints. Now constraints are 3x1 plus 7x2 less than equal to 50, 4x1 plus 3x2 less than equal to 100, 3x1 minus 4x2 is greater than 50, and let us say we have another kind of constraint which is 7x1 plus 10x2 is equal to 100. Now let us put some other value over here so that we do not get confused. Let this value be 50, we have 100, let this be 400, and let this be 200, 70, and instead of 400 let this be . Suppose we have this kind of primal. This is our formulation of a linear problem. We wish to convert this into a dual. This is primal formulation. We need to convert it into dual. Now, how do we convert this primal into dual? First thing is, before you convert a primal into a dual, there are certain rules there are certain prerequisites that we need to follow. First one is primal should be in canonical form. Before you could convert this primal into dual, your primal should be in canonical form. What is canonical form? Max and everything being less than. Ideally, it should be max with everything being less than. What is also accepted is min with everything greater than. So either it should be a max with all less than, or it should be a min everything with all inequalities with greater than type. This is canonical form. Before you could embark onto the journey of converting the primal into dual, this is first prerequisite, that the primal should be in canonical form. Z max with all less than or min with greater than. We have a max, everything should be less than. First constraint is less than, okay. Second constraint is less than. Third one is greater than, not accepted. Fourth one is equal to, not accepted. Also, in this formulation, there would have been x1 and x2 should be greater than equal to 0. These two constraints are not accepted. What can I do about these constraints? What I'll do about these constraints is step 1 in my conversion process. Step 1 in my conversion process would be that I leave Zmax as same 4x1 plus 3x2 subject to, I'm converting this into canonical form. Right now there are two constraints which are causing me issues. So I'm converting it into canonical form. What would that canonical would be? Max with less than. I have a max, very good. These two are less than, very good. No issues. 3x1 plus 7x2 less than equal to 50. then I have a 4x1 plus 3x2 less than equal to 400. This is greater than. What can I do with this? I can convert it into less than by multiplying the complete equation by -1. If I multiply this complete equation by -1, what happens is 3x1. Sorry, this was x1. This 3x1 becomes 3. This 3x1 becomes minus 3x1. Is that fine? I'm multiplying complete equation by -1. This 3x1 becomes minus 3x1. Minus 4x2 becomes plus 4x2. Greater than becomes less than, and 70 becomes minus 70. If you are confused why am I multiplying it to -1, you can understand it in this fashion. We have 3x1 minus 4x2 greater than equal to 70. Now I wish to convert it into less than type. What I'll do is, I'll pack everything and send it over there, and I'll pack this 70 and send it over here. Now if you are making this transformation, what happens? Changing the direction, this goes over there and becomes minus 3x1 and minus becomes plus 4x2, and this 70 coming here becomes minus 70, and this sign is sitting over there. Nobody has changed this sign. But in this process, what has happened? Minus 3x1 plus 4x2 has become less than minus 70. Minus 3x1 plus 4x2 has become less than minus 70. So either you can shift them this way, or you could simply go ahead and multiply the inequality by -1. This thing we have seen while we were solving the linear problems, or for that matter even graphical also. It is a prerequisite over there also, that RHS should never be negative. If it were a negative, we used to switch it, or we used to multiply it by -1. Here also we are multiplying it by -1, but not in order to convert it into plus into minus. Rather we are doing it to convert the greater than into less than. This thing is less than minus 70. This complete thing is less than minus 70. What has happened? Zmax is same. First two constraints are okay. Third constraint was greater than type. I converted it into less than type. This is the conversion of greater than into less than. Simply switching these sides. Obviously, 4a plus 5b is equal to 70. Can this not be written as 70 is equal to 4a plus 5b? These are one and same. What you actually did was, you took this over there. So it became minus 4a minus 5b. And this 70 coming onto this side became minus 70. And then you took minus common from all these. And then these minus signs cancelled each other out. So you ultimately got this equation. So switching the sides is okay. There is no harm in switching the sides. But when you switch the sides, your perspective changes. Now this 3x1 minus 3x1 plus 4x2 has become less than minus 70. So I have converted a greater than inequality into less than type of inequality. Second issue in this problem is, I need everything to be of less than type. One constraint was of greater than type. It has been taken care of. But then there is another constraint which is of type equality. What we do with this is, I'll split this equality into 7x1 plus 10x2. 7x1 plus 10x2. What I do is, I write it as, instead of this constraint, that is 7x1 plus, it was 10. 7x1 plus 10x2 is equal to 300. What I have done is, I have split this constraint into 2. What I have done is, I am representing this equation by two different equations. Now this representation stands valid only if we stick with the equality. In one case, I am saying this is less than or equal to 300. In another case, I am saying this is greater than or equal to 300. One equation is saying it is less than or equal to 300. Another equation is saying it is greater than or equal to 300. So, the only truth possible in these two conditions is 7x1 plus 10x2 is equal to 300. Now, this was reverse way of looking at it, that the solution of this will be this. Now, what I have done is the formulation of this can be this also. By formulating, by converting, by splitting my equality into 2, that is greater than and less than, what I have done is this is less than, this is greater than. Again, what I will do is multiply this to minus 1. Multiplying this to minus 1 becomes minus 7x1 minus 10x2 greater than becomes less than. This becomes minus 300. What I have done is I split equality into 2, that is less than and greater than, but then greater than are not allowed, so I converted that greater than into less than. So, these two are my valid constraints, valid split of my equality. This equality has been split into 2. How these two? Earlier I went with these, but greater than is not accepted, so I converted into less than. This is another conversion. Primal should be in canonical, max and less than. Right now what I am doing is I am converting this into max and less than. These were less than, fine. This was greater than, multiplied to minus 1. This is equal, equal should be split into 2 and then this greater should be converted into less than. So, I have my next constraint. This is my constraint, that is 7x1 plus 10x2 less than equal to 300. Then I have minus 7x1 minus 10x2 less than equal to minus 300. So, if we see, this is my first constraint, second constraint, third constraint, fourth and fifth are coming out of fourth constraint. This is conversion of whatever form is given into proper canonical form. This is canonical form. Max with everything less than. And of course, still this physical constraint stands valid. x1 and x2 should be greater than or equal to 0. So, with these steps what I have done is I have converted my given problem into canonical form. Now, I will convert this primal into dual. What would that process be? To convert this given primal into dual, the idea is we create a matrix of all this data. The matrix of all this data would be something like this. We have x1 and x2 only 2 variables. You could have more than 2 variables. We have a 3, 7 and 50. Then there is a 4, 3, 400. Everything is less than, so I need not mention it. Minus 3 and 4 minus 70. 7 and 10, 300. Minus 7, minus 10, minus 300. And then there is this one, 4x1, 3x2 and Z max. So, these are the values, 4, 3, Z max. Then we have certain constraints. All done? What I have done is, see, if you have seen the previous lecture, this is a reverse engineering of the complete process. If you have seen the previous lecture, we had a problem. From that problem, we came down to a table. From that table, we came down to problem formulation. This time, we have gone for the reverse process. I have converted my given problem into canonical. From canonical, I have formulated a table. And from this table, I can get into my dual. This will be the first step that I will be making towards formulation of dual. Now, I am starting my formulation of dual. Up till this point, I was only converting the problem for formulation of dual. This was only conversion. Now, I am actually into converting it. How that conversion goes? Now, instead of variables having this axis, I will be having variables on this axis, y1, y2, y3 and y4 and y5. Now, if these are my variables, what will be my objective function? We very well understand that the objective function comes from the variables, given variables. Earlier the variables were x1, x2, so my objective function was 4x1, 3x2, z max. Now, if these are my variables, my objective function would be 50y1, 400y2 and so on. So, my objective function is, this was max, in dual it will be min. Z min is equal to, instead of max I will be having a min, and this is how my objective function will come. Right now, earlier I was getting my objective function this way, 4x1, 3x2. Constraints were coming from here, 3x1, 7x2. Now everything will come row wise, 50y1 plus 400y2 minus 70y3 plus 300y4, and last one would be minus 300y5. Minus 300y5. So instead of max, I am having a min. Then the constraints would also be coming from here, 3y1 plus 4y2 minus 3y3 plus 7y4 minus 7y5 and 4. So my constraint would be subject to 3y1 plus 4y2 minus 3y3 plus 7y4 minus 7y5. Now it is a very straightforward rule that if everything was in less than, now everything will be in greater than. This we have seen in previous video where we saw the relationship between primal and dual. Everything less than became everything greater than, max becomes min. Why this is happening? You can check in previous video. That what is the relationship between primal and dual? Why is that relationship between primal and dual? This you can check in that video. Right now we are only seeing how to formulate this given problem into its dual. So I have 3y1 and so on. Because everything was less than, my constraints would be of greater than. Next constraint would be 7y1 plus 3y2, 7y1 plus 3y2 plus 4y3 plus 10y4 minus 10y5. Obviously, it will be greater than or equal to 3. And of course, y1, y2, y3, y4, y5 should all be greater than or equal to 0. Variable cannot be negative. My solution cannot be negative. Whenever I am suggesting a solution, this will be the cost, these many units need to be produced. Everything should be greater than or equal to 0. At most, you can drop down to a level of 0. You cannot get into negative zone. This is the idea of dual. This is my dual. Let us make use of this color. This was primal. This is dual of that primal. This is dual of that primal. Now, if you have a look at this, why at all do we formulate a dual? Why cannot I go ahead and solve this problem? Why am I converting this given problem into a dual? Just to put things in perspective, imagine if you were solving this problem. How many variables would you have? How many variables would you have? You would be having an x1, you will be having an x2, then there will be an s1 and s2, s1 and s2. This is greater than, so I will be having a minus s2 plus 8, minus s1, s2, this would be s3. I would be having an s3 minus s3 plus a3. I would be having s3 and e3. This is equality, so I would be having a artificial variable to start this. We are just seeing what the nature of the problem would have been, what the nature of the solution would have been. I would be having an s1 plus s2 minus s3 plus a3. because this is a greater than type, so there will be a surplus variable. With surplus comes an artificial variable minus S3 plus A3. This is an equality, so this will start with an artificial variable, so A4. And then how many rows? I would have had S1, S2. From third constraint, S3 would have been 0 and I would have started with artificial variable A3 and A4. This would have been solution of this. One of these would have been key row. How many calculations? One key row plus remaining elements need to be converted. If you remember the simplex, 1, 2, 3, 4, 5, 6, 7. I have 1, 2, 3, 4, 5, 6, 7. 7 in this row, 7 in this row, 7 in this row. 21 element operations. See, key row is straightforward. Key row is simply dividing it by key element. If you remember simplex properly. Key row simply is divide everything by key element. But for remaining rows, we need to go through those element level operations. What was that formula? That formula was new row is equal to old row multiplied by, minus key column element I multiplied by modified key row. This was an operation and we need 21 such operations each time. So 21 operations and one key row operation would solve me one table of simplex. But if we look at this point, my solution would be, let us make use of some other color. If we try to solve this one, if you solve this, your table would be in this form. You have one y1, y2, y3, y4, y5. You'll be having an S1 and S2. S1, S2, because both are greater than, you'll be having artificial 1, artificial 2. So this would have been my problem. And this time I would be having only 2 rows. 1 row and 2 row. How many calculations do we need this time? One key row calculation. Obviously, one of these would be key row each time. One key row calculation and then 21 element operations. This time I would be having 1, 2, 3, 4, 5, 6, 7, 8, 9. Only 9 element operations. So you can see the power of formulating a dual. If we formulate a dual, for each transformation, for each iteration, this is not complete solution. For each iteration, that is from converting first initial simplex table to second simplex table, I would need one key row transformation and 21 element operations. While in this case, when we have formulated a dual, what I need is, although my number of variables has increased, now I am down to 9 variables. Earlier I was only up to 7 variables. Number of variables may have increased, but the thing is that element operations have come down to 9 instead of 21. So this is the power of dual. And from where does this dual derive its power? The problem comes with number of constraints. If your primal has more number of constraints than number of variables, number of constraints 1, 2, 3, 4, 5, variables are only 2. If you have more constraints, your table will be very long. And when you have more constraints than number of variables, it is always suggested you go to dual. Because when we switch this to dual, it becomes 2 constraints and 5 variables. Earlier it was 5 constraints and 2 variables. Now it is 2 constraints and 5 variables. You can see 2 constraints are only 2 rows. Of these 2 rows, one will always be a key row. Key row operation is very straightforward. It is key row divided by key element in order to transform it to next table. So key row divided by key element, you move to next table. And then 9 element operations. But here you need 21 element operations. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 7 in each row. 21 in all. This is for one table. For complete iteration, you have 4 different variables. We can expect, on an average, we can expect 4 new tables. 4 new tables would mean 84 element operations. Here I have two variables. On an average, I can expect that there will be two tables. Two tables meaning 9 for first table, 9 for second table. 18 element operations. From 84 element operations, I am down to 18 element operations. This is the power of dual. This is the reason why we make use of dual. Yes, there is a shift in perspective also, but mathematically why we go into dual is, this is the reason. So I can put down when and why do we go for dual? When number of constraints is more than number of variables. Whenever you see that your number of constraints are more than number of variables, I have 5 constraints and 2 variables, then it is always suggested that you should go for a dual, because in dual your formulation would be so small. Instead of 5 constraints, instead of 4 constraints, I am down to 2 constraints. So this was it on conversion of a primal into dual. In next lecture, we will try to solve and we will try to see the relationship in solution between various variables x1, x2, s1, s2, s3, a3, a4 and so on. So in next lecture, we will try to solve a problem using primal also and dual also to see what are the relationships between the various results, how the results are found out, what are the relationships and so on. Fine. So this is it for our today's discussion. Until we meet next time, do take care. Thanks for watching. Bye-bye.